What the heck?
Tagon.
Sup fam, it's
Wacky Calc Wednesday!
And today we're doing a really cool integral. I'm not going to tell you what the answer is. You may have seen it before if you've scoured mathematical Wikipedia pages as much as I have. But I'm just going to present the integral and see if we can solve it. Let's go. Okay, so the integral that we're evaluating today is quite a strange creature. You might have seen it before, as I said. We're going to call this I, and it is going to be equal to the integral from negative infinity to infinity of 1 over e to the t minus t all squared plus pi squared dt. Now this is a strange beast, but I'm going to prove to you what it's equal to today. I'm not going to say what it is at the beginning. You're going to see what it is as the entire thing unfolds, and it's got a very beautiful answer. Let's just say it's in line with stuff that we've been exploring recently. So the way we're going to accomplish this is we're going to utilize a tool from complex analysis called contour integration and the Cochise residue theorem. So contour integration is like doing regular integrals but over paths in the complex plane, and the point is that if you do a simple closed loop in the complex plane around of a function around the poles of that function, you can add some amount related to those poles of the function together to get the value of the contour integral. And that's the essence of Cochise residue theorem. So what we're going to do is we're going to first figure out what contour we're going to be working this integral out over. So let's establish what contour we're going to be using. So we're going to be integrating this same function over some contour we'll call C. So we're going to be in the complex plane, so we're going to be using z to represent some complex number, x plus iy. And so we have this equation here, or this expression, I should say. And this is going to be the sum of two integrals over some c1 and c2 as well. I'm not going to bother rewriting every time you see me do this, just picture this function being rewritten. And c1 is going to be parameterized with t ranging from negative r to r on the real axis, right? So just from the number negative r to the number positive r. And c2 is going to be parametrized as the point t is equal to r times e to the I theta, where theta is allowed to range from 0 to pi. So what that tells us is that we're doing a counterclockwise contour integral, where the contour is, or a contour integral taken in the positive sense, where the contour is a simple closed loop that goes from negative r, so let's just draw the complex plane now. So here's the real axis and the imaginary axis. And essentially what it is we have a semicircle in the upper half of the plane that goes from negative r to r on the real axis, and then a semicircle with radius r from that point all the way around. So you could think of this point here as r times e to the I times some theta, where this is theta, right? And theta is going from 0 to pi. That's essentially the idea. And then we're going to let r go to infinity so that we end up with the real number line integrated over from negative infinity to infinity. And we're going to prove that the amount that the semicircle integral contributes goes to 0 as r goes to infinity. So that's the basic idea. Now, for a quick review of residue theorem, right, essentially what it comes down to is we're going to find points where this function, 1 over all this stuff in the denominator, diverges. So where the denominator equals 0 is essentially the idea. And then say this is z1, z2, all the way up to, zk, right? There's k numbers inside the contour that cause the denominator of the function under the integral to be 0. So what Cochise residue theorem tells us is, therefore, if we know that, if what we're trying to accomplish is the integral over some closed contour of a function f of z, and we know that f of z has poles at z1, z2, all the way up to some zk, right? So all of those are just different complex numbers where f of z is undefined. So if that means we can then therefore write f of z as some function g of z divided by the factor that is causing it for some zi, right? Zi where I is between 1 and k, right? Then the residue, by definition, the residue of a function f of z at one of its poles, z equals, say, zi, is equal to, I hope this is visible, is therefore is defined as the limit as z approaches zi of z minus zi times f of z, or the limit as z approaches zi of this g of z that I mentioned before, where g of z is just f of z, but without the factor in the denominator. So you could think of this as just being multiplied over, just leaving g of z. So that's why these limits are the same. And Cauchy's residue theorem says that the integral around a closed contour that encompasses some of these points is simply 2 pi I times the sum of the residue of the function at each of these points. And so that's essentially how we're going to establish the value of this integral here. So there's two things that we have to do. Is we have to establish which points will lie inside the contour, and then we need to let r go to infinity and show that the semicircle contributes nothing as r goes to infinity, and then we'll be left with the integral from negative infinity to infinity on the real axis, and we'll have our answer. So let's establish what the residues of this function are first. So what we're going to do is we're going to simply set the denominator of this function equal to 0, right? That's all we need to do, because we need to find out when the function will be undefined. So e to the z minus z, all squared, plus pi squared, can be factored using the sum of squares formula into e to the z minus z plus I times pi times e to the z minus I times pi. And remember, z is just some x plus iy because this is in the complex plane. So we'll say whatever the solution to this one is, we'll call it z sub k minus, because when we subtract the I pi over, it's going to be minus I pi, and we'll call this one z sub k plus, because you'll see that we're going to need different branches of a function, because we're going to need to employ a multi-valued function, and it's going to have these two potential options. So we're just going to call our solution to this one in general this, and the solution to this one in general that number there. I'll just show you the solution to this one, and you'll see how that one follows naturally. So we'll solve this one. So we have e to the z minus I pi equals 0. Adding I pi over, we simply get that expression there. Now we simply exponentiate both sides, as in raise e to both sides, and we get e to the negative z times e to the z equals e to the I pi, which is of course negative 1, right? And what we want to do now is we want to reciprocate both sides. So the reciprocal of negative 1 is just negative 1. 1 over e to the negative z is e to the z, and 1 over e to the z is e to the negative e to the z. Then we multiply both sides by negative 1, and therefore we have something times e to that same thing equals a number. So we want to employ the Lambert W function, right? So given that the reason I wanted to bring up the different values, indexes k, is because the Lambert W function is multi-valued and has infinitely many branches. And so we're going to be employing the Lambert W function and all of its many branches, because those are all solutions to the equations that we're trying to solve here. So I'm going to take the negative k branch Lambert W function on both sides, and I'll explain why. So we're going to do Lambert W sub negative k of 1 is equal to negative e to the z, right? Because we applied it to both sides of the equation, it cancels with this side, leaving us with just the thing that's being multiplied and in the power, and then we have w there. So we're going to multiply both sides by negative 1, like so, and then we're going to take the logarithm of both sides. So we're going to have z is equal to the logarithm of negative w of minus k of 1. So again, the negative k is just the branch that we're picking. So k is going 0, 1, 2, 3, and so we're just getting these negative branches, and I'll explain why. But now we're going to use log rules to break this up, so this is equal to log of negative 1 times, plus log of w sub negative k of 1. But, so what is log of negative 1? This is just I times pi, of course. And what is this expression here? Well, we know that w of 1 is particularly the number that solves this equation. So 1 equals w of 1 times e to the w of 1. So if we divide e to the w of 1 over to the other side, so we get e to the minus w of 1, and then take the logarithm of both sides, we get negative w of 1 is equal to log of w of 1. So we can just replace log of w of 1 here with negative w of 1. So this is minus w sub negative k of 1, right? So we're just utilizing the facts that we know about the Lambert W function to simplify these expressions. So that is to say that given that we have the plus and minus solutions and all of these branches to consider, the solutions to this equation, where we're setting the denominator equal to 0, are precisely the numbers z sub k plus or minus, so zk plus or minus, equal to negative w of 1 on the negative k branch, plus or minus I times pi. And those are all the solutions that will give us a pole of this function. The cool thing about picking this particular index is that the branches of the Lambert W function sort of go down as k goes up, at, like 1, 2, 3. So they sort of spiral down. So picking k to be negative as the index k goes from 0 to 1 to 2 to 3, right, up and up and up, will force all of these solutions to be in the upper half of the plane. Now, there will be the 0 branch, the 0th branch, the principal branch of the w function solution in the upper half, and it will only the plus version will be. The negative version will be in the lower half of the plane, which is not inside of our contour, so we don't need to consider it. But every other pair of residues for all values of k will be up there, and they'll all cancel each other, and we'll be just left with the principal branch residue. So that's sort of the argument that occurs here, right? We have infinitely many poles and therefore infinitely many residues to add, but every single one cancels except for the one at the 0 branch, k equals 0, which will give us a single residue, a single solution. So that's essentially the argument. So those are the residues, and now let's sort of explain why it has to only be the real number line and not the semicircle contour that gets infinitely large. So these are the solutions. These are all the residues we're going to have to consider. So when you're trying to prove that the contour, a certain contour goes to 0, or the integral over a contour goes to 0, you sort of want to parameterize the curve and show that as some quantity, like the radius of this semicircle, goes to infinity, that the entire integral's size gets less than any value, so it goes to 0. And if the size of a number goes to 0, then it itself must go to 0. Now, there's a certain level of pernickettiness you have to have with this argument here, because you have to make sure the contour goes between all of the poles, and so it never lands on one of the poles, and so you have to make very, very particular arguments, and I'm not going to go into that right now. I'll put a link to the stack exchange thing on here, on this subject. I'm just trying to present this in an easier way. So I'm going to present a sort of naive kind of argument that isn't quite exact or rigorous, because you need to consider the fact that the curve might land on one of the poles. So you need to sort of work around that by making sure it's between the poles, but I'm not going to do that here. So this is sort of just a naive argument. I will link to the more rigorous argument on Stack Exchange. So we're going to let z equal r times e to the I theta. Now the reason we're doing that is because this will make sure that the size of our number is r and that it's going along a circle as theta varies from 0 to pi. So theta goes from 0 to pi. Right, and remember, we're just looking at the semicircle arc here, so I guess I should say C2. And so we're just going to replace z, and dz becomes I times r times e to the I theta d theta. Right? Because we're just taking the derivative with respect to theta, because theta is the thing that's varying here. And so we end up with an integral from 0 to pi of I times r times e to the I theta, d theta in the numerator, divided by e to this z, so it's e to the r times e to the I theta, minus r times e to the I theta, all squared plus pi squared. So essentially what the argument comes down to is that you're going to show that the size of this integral goes to 0 as r goes to infinity. And the idea is that this has got, the absolute value of this has to be less than or equal to the integral of the, over the absolute value of the integrand by the triangle theorem, or the triangle inequality. And so we're simply going to take the modulus of the inside, and therefore we get the product of the moduli of all of these things. So we get the modulus of the numerator, which is, well, the size of I is just 1, the size of e to the I theta is just 1, so the numerator just becomes r, and we're being divided by the modulus of all this stuff down here, which depends on e to the r, right? And so e to the r is going to grow much, much, much quicker than r is, right? Because e to the r is exponential, whereas r is just a polynomial, a linear one at that. So the denominator here is going to get much, much larger than the numerator in size as r goes to infinity. So this is a sort of naive argument that this integral has to go to 0. So this goes to 0 as capital R goes to infinity. So this is sort of my basic argument that the semicircle contour contributes nothing as r goes to infinity, and we're simply going to be left with the real number line integral from negative infinity to positive infinity. If you want the full rigor of the argument that you need to actually do to prove this correctly, then go, I'll leave the stack exchange link in the description. Now that we've shown that the semicircle arc contributes nothing, and we've talked about the residues, let's combine those two things. So what we're going to do is we're going to find out what each, because now we understand that the sum, that the integral is simply, as r goes to infinity, the real number, the integral on the real number line, and that's just going to be the sum of all the residues inside that upper half plane times 2 pi I, right? So let's figure out what each residue is. And again, the reason we picked k in this instance to mean this, the negative of the index, or the negative of the branch number of the Lambert W function that we're picking. The reason we do that is because, therefore, essentially what you end up with is, and you can confirm this by simply plugging this into some calculator and figuring it out. If you consider these two solutions, z0 plus is in the upper half plane, and z0 minus will not be, right? Because z0 plus is negative w on the 0 of 1 on the principal branch plus I pi. Now, this is just the Lambert W function at 1 plus I pi on the principal branch. But Lambert W of 1 is just that omega constant, right? It's the number that solves this equation. It's the single real number that solves this equation, right? It's 1 equals omega times e to the omega, and omega is that number. So omega is about 0.567, right? And negative 0.567 plus I pi puts this number, z0 plus, squarely in the upper half of the plane. But if we do z0 minus, we get negative 0.567 minus I pi, which puts us in the lower half. So z0 plus is in there, and z0 minus is not. The thing about picking k to be the negative branch here is the negative branches are the ones that are higher up, just given by the math of the Lambert W function. And every single plus and minus pair of zk, where k is bigger than 0, are all in the upper half. And when you add all of those together, when we do the residue sum, all of those cancel, and we'll only be left with this residue. The one at we'll call it z0 plus, the one at on the principal branch of the Lambert W function. So that's essentially what the argument is. If you want to see the full rigor, see the stack exchange post. So from now on, I won't be writing W0 because we're just going to assume it's the principal branch. This is the omega constant, 0.567. So because we know that's the only residue that we have to consider, let's calculate the residue of the function at that point. So again, what's the residue? So we know it's going to be the residue of a function f of z at some point z0, right? That it's undefined. There's a pole of f of z at z0. This is defined to be the limit as z approaches z0 of z minus z0 times f of z. So essentially you're letting both of these things go to z0. So this goes to 0 because you're going to end up with z0 minus z0. And this, you're going to end up with the pole. So they're going to balance out and you're going to get a limit in that. And so that's the residue at that point. And because we know that the number we just derived before is the only residue we need to consider, we just need to calculate the residue of that function that we had as the integrand, but the residue at that point. So we're going to calculate, and you also have to multiply it by 2 pi I because of the theory of complex analysis. You get sort of a multiple of 2 pi I out the front. That's to do with contour integrals. It's a fact that I will cover at some point. So we know that this integral from negative infinity to positive infinity of dt over e to the t minus t squared plus pi squared has got to be equal to 2 pi I times the residue of 1 over e to the t minus t, e to the z minus z all squared plus pi squared at z equals z0 plus, where z0 plus was precisely negative Lambert W function of 1 plus I times pi. Right? That was precisely the number that we're plugging in. And so this is, by definition of the residue, the limit as z approaches this z0 plus of z minus z0 plus divided by this denominator here, because the numerator is 1, we just need to multiply this into the numerator. So we get e to the z minus z all squared plus pi squared. Now we're evaluating a limit of something divided by something else, both of which are going to go to 0 as z approaches this number. So we need to apply L'Hopital's rule, and so this will be the same as the limit as z approaches z0 plus of the derivatives of these two things divided by each other. So what's the derivative of the top with respect to z? Well, it's z minus a constant, so we just get 1 when we take the derivative. And in the denominator, we get, oh, I forgot the 2 pi i's, my bad. So there's 2 pi, I'll just put it in the numerator. So we get 2 pi I from the residue theorem, right? This right here. I forgot to write it though. 2 pi I. Now in the denominator we end up with taking the derivative here, so we have something squared, so we have to bring the 2 down and keep the inside, so 2 times e to the z minus z, and then we need to multiply by the derivative of the inside. And the derivative of e to the z is e to the z, and the derivative of negative z is negative 1. And so now, because z0 plus will not make this denominator 0, we can just plug it in without any problems. And so now we're finally going to evaluate what this integral is actually equal to, and it's a beautiful result. So we end up with 2 pi I divided by, this is a big denominator, 2 times e to the negative w of 1 plus I pi in the power, so we're multiplying by e to the I pi, minus negative w of 1, so plus w of 1, minus I pi. I hope this is all clear so far. I know it's very jargon heavy. And here we're going to get the same thing that we did here. We're going to get e to the minus w of 1 times e to the I pi minus 1. Okay, so that's a lot to take in, but it all simplifies very nicely. Because what is e to the negative w of 1? Well, remember, sort of by definition of what w of 1 is, it's the number that satisfies this equation, right? 1 equals w of 1 times e to the w of 1. So we can solve for w of 1 by dividing e to the w of 1 over. I'm going to change pens real quickly. Sorry, it's getting very dim, like it's not very bright enough to see. So we divide e to the w of 1 over, we get that w of 1 is equal to e to the negative w of 1. So e to the negative w of 1 is just w of 1. And e to the I pi is just negative 1. And here we have it again, right? We have w of 1 and negative 1. Which means we're left with, I hope I have enough room for this, we're left with 2 pi I divided by 2 times negative w of 1 plus w of 1 minus I times pi times the quantity negative w of 1 minus 1. Now, negative w of 1 and positive w of 1 cancel. And then we have negative I times pi, which can cancel with those two negatives there, times 2. And the 2's cancel, the pi's cancel, and the i's cancel. And we are left with the final number, the final result, which is 1 divided by 1 plus w of 1, or written maybe a little more beautifully, the final answer to this lovely integral is that the integral from negative infinity to infinity of 1 over e to the t minus t squared plus pi squared is precisely 1 over 1 plus the omega constant. And if we recall, just to be sure, the omega constant is about 0.567, and it solves the equation 1 equals omega times e to the omega. It is a beautiful, beautiful result, a beautiful answer to a beautiful integral, and I hope that this was a satisfying, if not thrilling, installment to the Wacky Calc Wednesday series. Thank you very much for watching. I have a cool response video coming for Papa Flammy at the end of this week. I think you'll find it to be a neat addendum to a recent video of his. It's like a temporary ceasefire before I break out the huge, huge guns for my next generalization bomb, because if you haven't seen his recent response, you should go see it. It's really quite cool. So again, thank you very much for watching. Bye-bye.